It is my pleasure to introduce Dr. Gopi Krishna M., Assistant Professor of Physics at Government Victoria College, Palakkad, with 13 years of teaching experience at both UG and PG levels. Dr. Gopi Krishna earned his PhD in microwave electronics and MPhil in physics, both from Cochin University of Science and Technology. His doctoral research focused on the radiation characteristics of planar printed UWB antennas with modified ground planes. Dr. Gopi Krishna has led a DST SERB funded project and is currently leading another at Government Victoria College. He has received multiple accolades, including the Young Scientist Award at the RSI International Symposium for his work on UWB antennas. Dr. Gopi Krishna was also awarded Junior and Senior Research Fellowship under UGC, CSIR, and contributed to the UK IERI project between CUSAT and the University of Surrey, London. He is an active member of IEEE and the IEEE Antennas and the Propagation Society, contributing to insignificant advancement in applied electromagnetics. I now request Dr. Gopi Krishna to introduce our distinguished speaker for today's technical talk, Dr. Jayakumar M. So please.
Good morning and thank you for that introduction. Continuing with the true spirit of APSYM, we have our next session expert, Dr. Jayakumar M., who is the center head of RF system and antenna design, Verdant Telemetry and Antenna Systems, Coimbatore. Dr. Jayakumar started his career as a scientist at Vikram Sarabhai Space Center, ISRO, and then he moved on to be the senior manager at Agrani Satellite Services in Mumbai. He had a brief stint in academic career at Amrita Vishwapeetham, Coimbatore, and then he moved on to become the center head at Verdant Telemetry and Antenna Systems in 2022. He has published over 100 research papers in leading national and international journals and has supervised 5 PhD research scholars and also contributed to India's first DTH services as part of private satellite operations and played a key role in ITU spectrum and orbital management discussions and has led multiple sponsored projects and international collaborations in academia. He is an active member of IEEE, and with that words, I would like to invite Dr. Jayakumar to handle the session. Sir, please.
So today this talk basically gives details of the industry trends of RF and antenna systems. Basically today I think many students, especially in the universities, you find this antenna design courses are getting closed many places, I think, including IITs, deemed universities and other universities. We found very few takers for this RF and antenna designs, but the opportunities and the industrial growth is just opposite. Today if you find, you see the growth in the RF and antenna is tremendous, and because everybody is going behind artificial intelligence, data science and related areas. So the real manpower requirement in this area is very limited, and today we are struggling to get people to work in this area, so we have to train them in a very big way. So that is a big challenge for the industries to get the products out in time. So today my lecture basically gives the industrial trends for these antenna systems, specialized antenna configurations, just simple literature review, and airborne antenna wake. That means basically we are our company mainly works with airborne antennas. So some of how the airborne antennas, how it's different from the normal your academic projects and other things. The evolutionary algorithmic approach is another one, which already I have delivered a small lecture here itself. That's the area we are also working, but it's more computational oriented rather than design oriented, but we got some good results. Some of my works I am going to show it. Active antenna design, evolution of smart antenna systems, that is what is the industry is today looking for. Beamforming antennas and antenna design, basically still the only area which is still analog. All other systems gone into digital. So this is only left out with the analog domain. So that is why it is more challenging today, because challenge is mainly how to interface with the digital system, with the antenna system. Till now, no antenna is coming out with the digital signals. That reason you know very well. I don't want the explanation. Yeah, this is basically the overview of this space, air, ground, sea, how this networking is done. And we have three different areas: space, air and earth. And all these communications are taking place through electromagnetic waves. I think if you are mapping the whole earth, you will find there is a big mesh of electromagnetic radiations around the globe, and it's just almost similar to a cloud on the earth. So this is what is the technology today is running behind all these things with the satellites, and more satellites are coming up. Private satellite industries are already coming up, and they are doing really well. And every system, you see, antenna plays a very big role. Without antenna, no, these systems will work, including your artificial intelligence. That is why many students may not be knowing the real importance of antenna and let us say it's electronics. Basically, the electronics is mother of artificial intelligence, because artificial intelligence never work without electronics. If your electronics is growing, then only your artificial intelligence will work, because artificial intelligence is very old topic, and when the VLSI systems are developed into the present stage of its that length and their technologies they use, that is why artificial intelligence are coming and easy to accommodate in the electronic system. That is why when the growth of electronics means it's a growth of artificial intelligence. It's not, the reverse is not correct. So antenna design is highly innovation oriented domain, because antenna design is unlike your digital systems. Antenna design need lot of innovations. Suppose you want to design an antenna for aircraft, that innovation is different from a ground station antenna. The antenna for mobile phone is different from other. So antenna need lot of innovations to accommodate in a particular application. These are the simple idea how these satellites are there in the earth, and how the electromagnetic waves and how the communication systems are established around the globe. And just imagine these electronic systems, the RF systems, the antennas involved in these interfacing all these satellites is very enormous. This is basically the growth of how these antennas has been considered in early 2000 to 2005, 2010, 15, 18, and 2024 and beyond. We are having artificial intelligence enhanced adaptive antenna systems, IoT in healthcare, and even healthcare also. We are moving forward with a lot of antenna systems. I will give you some small details. This is the industrial evolution, how this 3.0 and 4.0, 5.0, basically how it works with RF and antenna systems everywhere. I think 4.0 onwards, all the robotic manufacturing process or mechanical process, everything is attached with antenna systems, communication systems and digital systems. Then of course there's a computer. So all this interfacing need lot of antenna systems. The antenna plays important role in this industrial evolution. The industrial IoT is another antenna design, which is very, I think these things we have studied very long back, but today these are having a wider applications in the industrial IoT, having beamforming applications and each beam is addressing its host and how it performs and how the signals are transmitted without any interference. All these are having this, all very simple things which today it is happening, and this is how the autonomous industries are there. I think if you are going to Chennai Hyundai car factory, most of the processor they are using with robots. All the robots have more than 20 to 30 antennas mounted in various locations. All these antennas are directly connected by externally like this beam steering antenna systems. Through that only they controls, receive signal, transmit signal, and control the whole process. And smart systems, these are the basic systems used for mainly based by antennas. You can see how this system now evolving with more and more RF and antennas. My importance of giving all this, not to give these applications, but just to emphasize how this antenna and RF systems are involved with all these systems. It is now, you can always tell that there is a, today I think the latest car, normal car, you can see they are radar fitted cars, and other cars there are some sensors they use. Mainly they use antenna systems for communicating from one end to other end. So everywhere these antennas are mainly used, and this need lot of innovations. These are the other areas. Okay, some of the specialized antennas which my work as well as the others work which I have just given like this. So how this antenna we are evolving as the academics as from the industry. So basically if you are looking at this diagram, this particular one is a cycle, product cycle it's called. Basically in any academics, it starts from definition, concept, and just product design. Then you will go for a publication. You never bother about what is, where it is applied or whatever. So the academic stops at the first three portions. So if you are going to industry, then you have to go for prototyping, testing, certification, manufacturing. These processes are very tough project compared to this design. You can design an antenna very quickly, within 1 or 2 days you can get an antenna. But the whole process coming to the manufacturing stage is not easy. Today you design an antenna just assuming that infinite space in a HFSS or CST you are using, and your antenna will provide a very good gain and very good radiation pattern, beam width, bandwidth, return loss, or everything. But once that antenna, if you are mounting on an aircraft, it terribly fails in the radiation pattern, gain, and all other parameters. Whatever you have published papers in IEEE and other journals will not show when the same antenna is mounted on an aircraft or any other application, because antenna is influenced by the ground plane. What type of ground plane you are using, which you never tried in your research, you never tried in your paper. You were told you have designed a new antenna which is working well and it shows like this. The same antenna will not work on an aircraft. So we have seen many. We used to design antenna, we used to nowadays we used to incorporate the aircraft body, a portion of the body also in our design. But that takes more time for our simulations. Even it takes 24 hours, 72 hours also sometimes to get the simulated results out. So that are the things we have to consider for industry point of view. So project and product are lot of gaps. The gaps are, we have to fill it. That is, every academician has to play an important role in making that this is what is the skill and the degree. Degree and skill, they are totally different. The skill, see, without degree a person can work very nicely. With skill, and he cannot meet anyone else. Skill is very important, because in our company we have interviewed around 10 to 12 students from BTech, after 7th semester, I think nearly 5 or 6 EC and others are electrical. And I could shortlist only one electrical student. He can do our programming, simulation, and all these things. So that is a way. So degrees not matter. Skill and understanding the technology is very, very important than just getting a degree. Yeah, these are some of the simple structured antennas, how we are getting into some of the papers. We tried some of the antennas in our product point of view. Nothing has been worked actually, except some of the, I will tell you. These are the simple structured antennas which published in, I think you can see the journals are very reputed journals. And this is the second one, the last one, 2019 IEEE Access is our paper only. One of my PhD students' paper. So that antenna, we designed the antenna for a particular application. So it works very well. So you see, when you are application oriented, it will work. Otherwise, it will fail. These are the combinatorial structured antennas where you will find lot of shapes, this is all they to get publications, to get acceptance quickly. So they think that there are a lot of innovations, but you cannot use it for any of our products because these are highly influenced by the external objects because of the slots and other shorting pins and other things they use in most of these things. Okay, let me go to the airborne vehicles. That is our prime area of our work. Basically, most of you know the radiation pattern of an antenna system. You will find the radiation pattern is considered from a coordinate system. This coordinate system, you are considering this is the coordinate system. I think everybody knows that is Z axis is always taken as the transmission direction and X and Y direction. And you have different planes of radiations, XY plane, XZ plane and YZ plane. And always you assume this antenna is at the origin. So this is what is we assume in our simulations also. So simulation you have to start, the antenna center is mounted on a 0, 0, 0, that means there, from there the whole radiation pattern we have to take. Then only your radiation pattern will show the actual result. But in the airborne antenna, you see the antenna is mounted on an aircraft. And the same radiation coordinate system is also on the aircraft which is moving. So now your ground system, this is a ground antenna which is tracking, this aircraft. You are designing an antenna on the aircraft that the entire coordinate is moving, and you are at the ground station. So you will have a radiation pattern already taken, which you can see here. The radiation pattern you already evaluated on the antenna system, but you never taken a radiation pattern with a moving aircraft condition. So when the aircraft is moving, or when a rocket is moving, or a missile is moving, the coordinate system also moving. So when you are looking from the ground, the look angle falls on the coordinates, moving coordinate system in a particular angle, x, y, z you can see, or you can take theta, phi and other variations. That radiation pattern may not match with the your actual radiation pattern. Okay, so you have to go for a new radiation pattern, new identification of the signal analysis. So how the signal reception by the tracking antenna or transmitting antenna, you need something new, extra things which are not available in any of your academic system. So what we do is, we used to take the 360-degree radiation pattern, complete radiation pattern, real radiation pattern. It's not a simulation. We make antenna mounted on a plane, then we rotate it all 360-degree throughout actually. So you will get a spherical radiation pattern. That spherical radiation pattern we put it in a Excel sheet data. You will get a huge database actually, and that database and there is a coordinate mapping database is provided by the user. User will provide this is a rocket trajectory, or this is a flight trajectory, like that. So every moving object will have a trajectory, definite trajectory. We have mainly our projects are related to that only. So naturally we can map it. So we use an algorithm. That algorithm will coordinate to coordinate. It will get mapping. It's some telemetry functions we used to add here in the programming, so that we use some MATLAB or Python program, so that it convert that into this one. So finally you will come out with a radiation pattern. This is a typical radiation pattern when you are looking from the ground station. So I am constrained to give the details of the names of the flight and other things, because I can't provide any detail. This is a monopole antenna mounted on an aircraft. Okay, a moving object. Let us assume a moving object. So you can see how the gains are plotted. You can see the red color. These are the mapping areas where x-axis, y-axis, pi and theta of the ground. So you can see the radiation pattern, and the yellow regions are, I think, less gain. Accordingly, the signal level, where you can identify where you will get a signal cutoff. So wherever the green points are there, these are the dark spots. We can find there is a possibility of a signal cutoff from the aircraft. So like that. This is a monopole antenna, and this is the microstrip antenna on this one. You can see the difference between monopole and microstrip. Monopole have wider omnidirectional in all directions, but microstrip have nulls at the back side, so you can see lot of nulls here. So from this, the user can identify how this gain and other things he can locate, and he can find out how this entire flight and how much this antenna performs. So these are the simple. I am just giving examples how these are varying and how the skill set has to be improved in such areas. This is another one which even today our ISRO also doing this almost similar exercise. We have developed, actually during when I was in ISRO, I have developed this particular coverage factor calculation. This one very difficult, because if you have a wraparound antenna, most of you know what is a wraparound antenna. Wraparound antenna is mounted on a moving vehicle with around its body fully. So it does have a omnidirectional pattern, and maybe there is a null at the axial. You can see this simple example only. So where we do, you take the spherical radiation pattern again, then there is a coverage factor computation algorithm. There is a simple algorithm, so we through some integrations of data, again Excel sheet, Python, and we can do some calculation. Then you will get a graph like this. This is the radiation pattern. This graph, this graph, this one gives the this is basically radiation pattern, which gives how much the gain and how much its coverage. Okay, so you can see the 100% coverage means you have minus 14 is the gain, minus 13 to 14 is the gain. That means throughout you will get minus 14 is ensured, your antenna is having a gain. But if you want 0 dB gain, you are getting 60% coverage only around the object, which is the moving object. Around the object, 60% only. Now you can improve your design by making this high gain areas to go up, more challenging, and the design also have more complex, so you can improve like this. So these are the various challenges in the industry which we are facing in the airborne antennas. And another area which we have already started is another area, because one of my PhD student already got a degree in this area, evolutionary algorithmic approach for antenna design, which basically we got inspired from a NASA's work. I think 2011 or 12, they published a paper, this evolutionary algorithm approach. In fact, I have associated with one of the projects from Cochin University for this same project, and they did well, good projects actually. So this is another area where today this machine learning and deep learning or other type of learning optimizations, everything can be brought in the RF antenna design. So here evolutionary algorithms, basically as a RF person, I was not known to evolutionary algorithms, so we approached the computer science department. So through computer science person, we have collaborated some work. So continuously we learned each other, and we brought we have developed algorithms from the multi-objective evolutionary algorithms and other type of algorithms. Several algorithms you can see here. This is how the concept works, and because I cannot spend more time on these things because it need minimum 1 or 2 hours of explanation only for this one. So I just give you the basic things. How antenna system, maybe we are considering a microstrip based planar structures. It is not applicable for 3D structures, only 2D structures, microstrip based. So microstrip based, how it is considered, and the 0 and 1, how we can remove the metallic portions and how to optimize it. So this is what we made, and the picture you are showing, it is shown here, is developed by NASA. How the monopole, normally monopole means you can see the normal monopole, and how much bends they have created using evolutionary approach, and now we got a very good performance. But the thing is that this may not be applicable for their application. So this is the optimization. So I will give you more details. So this is what is we have developed actually from a antenna point of view. We have made all these procedures, these algorithms we made, and finally I will show some of the results. This is what we constructed the whole project actually. So we have HFSS, we have MATLAB or Python, not both, MATLAB or Python, and we have some structural optimization. Actually, we have connected this Python program with the HFSS. And we generate nearly 100, 200, even 10,000 samples also. That means 10,000 designs. Basically, you design HFSS for 1 or 2 designs, 1, 2, 3, 4, maximum 5, 6 designs. You will come out with some good results. Here we even go up to 10,000, and 10,000 means naturally it takes days to get out of the results. So we use high speed processors system which we had available. So when you connect this particular system, we continuously supply and we modify the structure of the antenna, and once it is converged with the input values, fitness function, we call as a fitness function. Fitness function means it gives the boundary condition values, like what is the return loss you expect, what is the bandwidth you expect, what is the frequency of operation, what is like that, any parameters you can define. So all the parameters are defined, all these parameters it will work. So HFSS will work. So there is no human intervention for this process. Continuously the HFSS will take the data from Python, and HFSS will simulated data will be fed back, and it will be analyzed by our program, Python program. So Python will tell no, we are not reached. Again we give back the new data, and new data will come back. So continuously this process. So ultimately finally when reaching, and we give not only fitness function, also we give some ranges. If you cannot define the actual value, then your program will not converge. Okay, it has to converge means you need some, you have to provide some ranges. So within the range means naturally you will get a structured parameters. So basically you will get like this. What NASA has got this data. This is we got it from our point of view, what the new structures, And this is our one of our students, BTech students project only. The first one, this is the antenna which this is the antenna is the conventional microstrip antenna, and after this 100, because here we use 100 designs. 100 design means 100 rotations of 100 iterations we have done. So finally you see the new shape of the antenna is like this, with a wider bandwidth, and you can see the return loss value almost it's fully matched condition, and gain also a positive gain from the negative gain. The conventional we got -2, and in the optimized structure we got positive 1.2 gain. So that is a thing which we achieved from our program. This program is flexible. Don't think that this is a definite program. You can use a lot of innovations to add on this. Inside that you can use machine learning also to identify certain new parameters, so that you will get some more innovative ideas. So these are some of the structures of the band pass filter, which is we collaborated with ISRO Bangalore. So ISRO Bangalore wants a filter using evolutionary algorithmic approach with their parameters are beyond the imagination. Deliberately they given that parameters because they thought evolutionary approach only it will come out with some good results. Still we could not get it actually. So here are some of the things we got, and we tried with the traditional filter and we introduced this structure inside. This is another innovation we have added here. We got somewhat good result. Actually they want some cutoff, rejection ratio is 110 dB. That is beyond, I think you will not find in any industry people make filters of 110 dB rejection ratio. ISRO has put pressure on us to get a 110. It is impossible to get because we have gone through all this literature survey. We got maximum 90 to 100. That also using waveguide based filters, not the microstrip based filters. So we are able to achieve nearly 75 to 76 dB using this wiggly structure. This also we evolutionary approach only, and we got a very nice curve, and we fabricated, we tested it, and it was going almost one-to-one matching. And such a structures we can't imagine just by design a filter. You can see this, all these bendings and all the curves and everything is the after hundreds, 200, this is I think nearly 600 iterations we made with the HFSS, and finally we got a good result and comparable result. Now next is the active antenna design, evaluation to a smart antenna system. This is what is, I think should repeat, our Ajit has already given lot of details. That is more detail. Here I am not going to. I am going to give only the hardware point of view and how the antenna systems are played the role in the smart antennas. So basically you see active antenna systems are the essential things today. Today nobody makes simple antennas. Any antenna you take, whether it's a GPS antennas, a small antennas, or any wearable antennas, or any Wi-Fi antennas, they are associated with some either low noise amplifier for the reception or power amplifier for the transmitting. So it is all associated, integrated also. So you have two different type of systems. One is the low noise amplifier alone. So what you will get is the improved signal, same RF signal will be available at the output. The other one is low noise block. So first is low noise amplifier, second one is low noise block. Low noise block basically comprised of low noise amplifier, local oscillator, mixer, and IF amplifier. So basically you will get the IF signal output. Okay, so these are widely used everywhere, and this low noise block and low noise amplifier based are today is the major topic of design, and there are many good chips are available. You don't need to worry about designing each and everything. These are very small chips available in the market. And the basic concept of this active antenna is, you know very well the noise. I don't know you know about this, how this noise is generated in a system and how the noise is coming from the outside. The noise generated from outside, noise generated by the system. So these two things are big problems for our design. Any amplifier design, you will have a lot of difficulties in achieving the requirements, especially the noise level, because of this noise issue. Noise is a natural phenomena. You cannot make it zero. Always noise will be there, either internal noise or external noise, always there. So in this equation, I just wanted to mention how this noise is related. Actually, noise is nothing but KTB. K is the Boltzmann constant, T is the temperature, and B is the bandwidth of the system. Here, the only parameter related to the electronics is bandwidth. So if you are making a wide band system, means you are making a source for wide noise also. And naturally the temperature and noise are interrelated. The temperature increases, noise increases. I think you know very well, if you have studied the basic physics, and the temperature increases, minority carriers in the junction start increasing. That creates its own current, and it's in any directions. That makes noise. That is a noise signal. And if there is a noise signal generated, naturally the temperature of the junction increases. So both are interrelated. So always if there is a rise in temperature, the noise is generated. When the noise is generated, rise in temperature. These are related. That is what is the temperature and how this is calculated here. So this is, I just wanted to show how this noise, and how we can reduce the noise. We can make it zero, but we can reduce the noise. You can see the second equation, this equation, second equation, that shows that the first system, F1 belongs to the first system, F2 is the second, F3, like that goes. It's a series, and the first system determines the noise of an overall system. Even though if you are making a very bad amplifier at the second stage or third stage, doesn't matter. Your first stage should be a good noiseless system. That is why low noise amplifier is used with antenna systems. Sorry. So any signal coming from an amplifier, the first system we attach with the any antenna system. So the antenna and the first system we are combining means, so after that you are using a receiver or anything, your noise is minimized, not completely zero. Okay, and this is how, sorry, there is some mistakes in the block diagram. Here you see the receiving antenna, and we use SAW filter to reduce the bandwidth. First thing is to reduce the bandwidth, means you are almost trying to reduce the noise also, because KTB, that equation, so noise is reduced, so finally you are getting a good signal. And there are another type of diplexer filters are available. These are very available in the market, which we widely used in our design to mitigate the noise problems. So this is, I think, DTH system, because I already worked in DTH in one of the companies. So basically those days, before introducing DTH in India, we were having a lot of discussion with France for making a very good set-top box for India. So that time there was a discussion with the set-top box similar to a mobile phone. So you can only use the SIM card and you can reuse it. Mobile phone you don't need to buy. SIM card you have to buy for changing your operator. But still today in our set-top box will not work for if you are changing the operator. That is a different one, different politics actually. So once you can see here, the satellite signal is falling in the range of 10 gigahertz, which is coming at the feed point, that is where the antenna is there, and the feed point is also associated with, attached with the low noise block. It is not low noise amplifier, low noise block. So basically you are getting a signal of 950 megahertz to 2.1 gigahertz signal range which is coming to your set-top box. So this, another importance of this, this is the cable noise. The cable attenuation is nothing but noise. You can see the equation. The loss, you can put it into noise. So finally you will get loss equal to noise. So cable attenuation is 2.2 dB per meter at 10 gigahertz. The same cable, if you are using it at the 950 megahertz, you will get 0.04 dB per meter. That is why today you can run hundreds of meters of cable from the terrace to your home with a set-top box without degrading your signal level, because your low noise block is attached with the antenna itself. This is a simple active antenna circuit, which I don't know how many of you know it actually. We are talking about LNA. You cannot connect only LNA with the amplifier. It is very, very difficult, because LNA is not, it will amplify the signal, but you have to use a band pass filter at the beginning, at the end also, to reduce the bandwidth of use. What is the bandwidth used for your application? That has to be added here, so that you are considerably reducing the noise level, and you are using a bias T to give the powering the low noise amplifier. So you have to give a power. You cannot run the separate cable for the antenna mounted in some locations, any location. So same RF cable, you have to use it for that. For that also you need a solution, that bias T, then DC-DC conversion. All this has to be put together. It will go to the whole active antenna. So if you are looking at the active antenna, means this is the basic building block for any active antenna. This is the evolution of active antenna to a smart antenna, and here many places I think we are using it actually. Normally simple active antenna is LNA with antenna. You will get RF signal, same RF signal you can receive. Another is IF signal you can receive with a low noise block. Next you can use the receiver also attached with that, so you can use that. Second one is A2D conversion, also you can add with the antenna. This is all integrated version. Don't think it's all connected with the cables. They all in a single pack. Receiver with the ADC and everything here is connected, and you will get digital signals. Then signal processor also attached. So how these antennas are getting evolved? So that is what we are using software defined radios. And today software defined radios are coming because the integration of antenna systems, analog systems with LNA, and digital systems, mixed signal systems like ADC converter, DAC conversions, and signal processing part. All this makes a very good software defined radio. Once you have software defined radio, an array of software defined radios gives the smart antenna solutions. So this is how it is different. The software defined radio with analog and digital radio, and you see this particular one, you see these many parameters are programmable, which we can't even think. Even when I was studying, I never thought that this, like modulation type and bandwidth, they can be programmable. Today everything is programmable, and there are good scope for in this field. These are different areas where the industry is now looking for. This is a simple block diagram. Already I think our previous presentation, they have already shown everything. These are already there, and this is what is one of our product basically. So we are using similar kind of system with FPGA, with RF SOC and other things we combined, and some user interface. So many things, activities are going on with the software defined radios, and it's all highly integrated, and the whole system is falling with the maybe 15 centimeter in the 15 centimeter board. You will find 4x4 element antenna systems with the whole electronics fall in that. So we can see the integration, the level of integration we are going. It's very, very beyond our imagination. The integrations are there. You just see the simple software defined radio. you can make your software driven radio with the antenna and other things. You can learn how this software driven radio and make it integrate with your laptops. So you can program it, you can control it, you can make arrays of antennas and control the array, beamforming. All these are possible by normal students actually. So beamforming also, you can see how the analog beamforming, we can use one SDR, the whole beamforming is possible. But but what we are doing is, this all the phase shifters we are using it here is analog signal. Okay, this have a lot of limitations, but in the digital beamforming, each antenna have an SDR. Each antenna is associated with SDR, and each one is getting programmed, and we can use a laptop to control these SDRs, so that you can make different type of beams. And I think your normal USRP kit with the GNU radios and other things, so many projects you can do it like this. Here the phase shifts and other things are digitally created, not the analog creation, because here the phase shift is coming under computation. That means part of the programming, it is not related to hardware. In the analog beamforming, the phase is hardware part, and the phase also having some limitations, and the beam steering conditions, side lobe suppression, side lobe creation, all are very, very complex. So these are the various advantages, disadvantages of this analog and digital. I think you can get it from any resources available. And digital beamforming, of course, today is the hot topic in our products. Even our Indian defense is mainly looking for this digital beamforming systems, because we had recently discussed with some of the defense labs in Bangalore. They all wanted to replace this existing analog beamforming systems into digital beamforming. So you can see how much the variations are happening, and digital beamformings are easy to implement and easily controllable and programmable, and resources are available. There are open sources are available, and learning also easier. And once you understand the electromagnetic basics, the antenna characteristics, and other interfacing things, then the topic is very, very, very interesting. This is some of the recently one publication we found how this antenna, array antenna, they made into a beamforming system. And just I wanted to show how people are working in various institutes and industries with developing very, very compact systems. These systems are very compact. Don't think it's looking like a very, very complex and big system. It's not a big system, very, very small system. And this is one of our project only, not from a Verdant project. This is basically prior to COVID. I started a small startup when I was in Amrita. Actually, we 5 people together, we started a small startup those days. I think 2017. And those days we had a very good discussion with one of the defense lab in Bangalore, and they wanted to have some system. So I just want, deliberately I'm avoiding the names of the system and other things. They want the ADAR 1000 based chip. This is chip actually, analog devices chip based programming, this radar system, which we have completely developed, and the programming also we have developed. When we about to come out, the COVID started. So everything is closed down, and labs closed down, funding closed down. In fact, many things happened. System remain hanging today, and this is how we developed actually. Even we started with the normal antenna designers, RF designers, and you know how we have landed here with digital systems, and how this interfacing and other microcontroller based programming, and then how it is getting controlled and landing and everything. And recently ISRO has successfully completed this project, and they used in their Chandrayaan, and they demonstrated also. This is our system, the antenna system arrays. I think there are 4 arrays integrated, 4 into 4 arrays. Each array is connected separately and connected to ADAR 1000. ADAR 1000 we programming it, and we can control this beams receiving, transmitting, and get the signal with the Doppler shift. And we used to calculate the distance, altitude, everything. So this is 4G to 5G. That is what is today's things. I think you know very well all this. What 5G provides and what 6G provides. I think 6G research and testing is already started by many communication companies. So basically the challenges beamforming in 6G. 6G is very, very important. Here how I think how this is connected. This is one of the antennas. Now one of the companies, they wanted to connect, make this antenna home based. Today what we are seeing here is the base station is directly connected to a home through a fiber optics cable. Now then router do the rest of things. But in 5G what we are going to do is the base station itself is a massive MIMO system which some of the beams will be connecting directly to the home antenna, and from home antenna you will get 60 gigahertz Wi-Fi, and all the systems are connected, and the networking also different, standards are different, and we are replacing the old technologies, all the existing 4G, 3G, everything. So here we are device to device communication, mobile to mobile communication, laptop to laptop communication, everything. You don't need to have a base station or external things. Suppose you want to call a friend inside a room, still you have to call the base station. Through base station only you have to call, but in this internally you can communicate. It acts like a local communication system, intranet connectivity type of things. So these are the commercial applications what I think many people are interested actually. These are the new trends in the antenna systems, reconfigurable antennas. Basically the adaptable wireless networks, smart systems. The reconfigurable antenna systems is basically associated with the active antennas. Okay, it is not only antenna system, it is associated with signal processor and other things, so that you can reconfigure the beams and other things and characteristics of the antenna. AI enhanced antenna design, that is also now mainly used in industrial IoT and autonomous systems. You can see in the automobile industry also there are advanced ADAS based automobiles already available in the market. You'll find some of the cars, it can go into a cruise mode by identifying the objects and identifying the lines and identifying the other things they take into account, and continuously they update the data and redirect the engine system, steering system. So these are several type of antennas are mounted in several locations which take care of these things. AI enhanced antennas. Metamaterial based antenna system is not new, but still you will get a wider aspects like smart homes, medical gadgets and wearables. They use metamaterial antennas. Energy harvesting antennas, Rectana is mainly I think most of the RFID tags are used these Rectana devices. Flexible and stretchable antennas mainly in the healthcare, sports and other thing. Basically in Coimbatore there is one industry. They are making some gowns for textile industry, gowns for this medical applications. They also added some of the antenna system with the chips embedded on that. Actually that antenna and embedded important one, but they are able to make it with their stitch along with their cloth. So that also now in the market actually. So healthcare is mainly used, and these all developed after COVID. That is very important actually. Before COVID these things are not that much come out, but today it's the exponential growth of technological applications coming in the market because of the innovations. Low profile conformal antennas, I think mainly used in aircrafts, rockets and other places, and biocompatible antennas, implants, most of the implants also associated with the antennas, and also there is low noise amplifiers, other amplifiers and battery, and how the antenna design is different, because the antenna design is with the superstrate as a live tissue. They made it like this. We also done some research on that, because some requirement on implantable antennas. So what we did is we bought some chicken pieces, and we use chicken tissues, because we can't use human tissue. So chicken tissues we use, and on the microstrip antennas, and we found some good results. Actually, it's we are getting signals transmitted. Then we have to map this chicken tissue with the human tissue. That is very complex, because that we have to give to some medical researcher or medical professors. They have to do it, how these tissues are related, and how the blood is influenced on this radiation pattern. All this, a lot of good scope for this research in this area. So these are some of the commercial applications of antenna systems are there. The smart antenna market today, I think MIMO, massive MIMO and all these things. So with this I just conclude. Any questions I can answer.
Thank you, sir. Now the stage is open for discussions. The participants are encouraged to interact with the speaker.
Sir, regarding the evolutionary algorithm, so we can make complex structures in the simulation, but what about their fabrication and their later maintenance? So how will it affect it?
Yeah, this is very simple, because fabrication is not matter, because I already told this is not 3D structures, it's all 2D structures, microstrip based. So any type of structure, you can photolithographic will do it. You give a structure, you get the Gerber file and transmit, you will get the structure fabricated.
Like the structure you showed earlier, a wire monopole antenna, that was
monopole antenna. We have not made a monopole. That is, I think, the publication by NASA. They made a monopole. I think they started their research with a monopole antenna, and they started bending it. Okay, so they made a simple wire and started bending, and they got some good results. So we inspired from that research, and we done work with, because we don't want to do it with the wire antennas or 3D structures like waveguide based horn antenna type of things. We want to do it with the microstrip, because we wanted to use HFSS or CST. So we found it's convenient to use microstrip, so we found, and fabrication also.
So another question I had was regarding the parameters that we have to take in account for in the HFSS, so that so what will be the optimum number of parameters, or what are specific parameters, so that we can get a proper convergence of the proper antenna that we need?
You have to apply certain rules here. Actually, you can't consider imaginary level of considerations. First of all, if you want an antenna to be good matching with the particular band of frequencies, and the maximum size of the antenna should not go beyond or this much only. And material, like I had only RT-Duride material, no other material, so I am fixing it, that RT-Duride material. So certain parameters you have to fix it. You cannot make imaginative values of impedance matching or imaginative values of bandwidth. This is not possible. Okay, not possible means it will not converge. It will continuously, it will run. You will not get any result out of it. So if you want to get a good result, you minimize the number of parameters, then you slowly increase. You start your programming with a minimum number of parameters, then you slowly take freeze other parameters, then the third parameter you make it variable, then your evolutionary algorithm will work very nicely. Okay, so step by step you have to go.
So you have to make it in stages. The parameters, first select a few parameters that you want to be absolutely true in that antenna. So then you get a converged antenna, then use that antenna as the next step for covering all other parameters.
Yes, then you go to next level. You can change the level from one point to other.
Thank you, sir.
Don't do it at the first time itself, all the parameters.
Thank you, sir.
Yes, okay, thank you.
Thank you, sir. That was an informative session. We are now honored to welcome Dr. Gopikrishna to present a token of appreciation to Dr. Jayakumar M for his valuable contribution to today's session. Dr. Gopikrishna, please join us on stage.
Sir, that indeed was a really insightful session on your experience on antennas and propagation. On behalf of all of us from APSYM, we thank you for doing this session, and kindly request you to kindly accept our token of appreciation.